Good evening, everyone. I hope I am audible and the slides are visible. Can someone just confirm that once?
Yes, sir.
Okay. Okay. Thank you for confirming. And then I think we can start with this week's tutorial. So, yeah. As usual, we'll have the same format where I'll show you a question. You take some time to answer those questions and then we can discuss the answers. Okay. So, here is the first question. Which of the following can be the solutions for password leakage problem in database servers? The first option is two-factor authentication, password plus OTP sent by SMS. The second is storing encrypted passwords in database and in scripts. The third is using the same password across different sites. And the fourth is single factor authentication using username and passwords. So anyone who would like to answer? Okay, so A is one correct answer. There's another correct answer. So can you guess what the other answer can be? B. That's correct. So both options are correct. Okay, option A and option B. All right. Let us move to the next question. So, in a file structure of variable length records, which of the following does a slotted page header contain? The first option is block pointer. The second option is number of record entries. The third option is end of free space in the block. And the fourth option is size of the next record.
Option B,
Okay.
number of record entries.
Okay. Is that the only correct answer? So option B is correct actually, but there's yet another correct answer. Okay, uh, so the correct answer is option B and option C. That is number of record entries and the end of free space in the block. And this diagram has been taken from the class lecture. So if you have any doubts, I think it would be best to go through the lecture once again. Okay. So moving to the next question, which is a numerical question. So a file organization is sequential and unspanned. That is, one block can store only whole records. That is, you cannot have partial records stored across blocks. Okay. Now the disk block size is 512 bytes. Each record of the file is 32 bytes long and the block pointer size is 12 bytes. The question is, how many records can be stored in one block?
We can enter max up to 16 records.
Okay. So how do you get the answer 16?
If the block size is 512 and
Mhm. Each record is 32 bytes.
each record is 32 byte
Hmm.
and pointer size is 12 bytes. That's
Mhm.
why.
Okay, so what calculation did you do? Was it 512 divided by 32? Okay, is there anyone who has a different answer? Okay, so I do not know if the answers over here are for question 3, but is there anyone who agrees with answer 16, or is there anyone who thinks that some other option should be correct? Okay, so first of all, it is given that the file organization is sequential in nature and is unspanned. So we saw that with unspanned organization, you can have integer number of records in a block, right? So you cannot have like a half record in one block and the continuation of the same record in the next block. Okay, so that is what unspanned means. So a block is either entirely present or entirely absent. It cannot be partially present in a record. Okay, then the second keyword is sequential. So when we say that file organization is sequential in nature, what we essentially mean is that each block, first of all, has some number of records, and then there's also a pointer that shows which block do you want to access next. Okay, so this is very much like a linked list where you have some data stored and then there's a pointer to the next block as to which block should you access. Okay, now that you know this, uh, now that you know that a block has some unknown number of records, each of size 32, and a pointer that is of size 12, then how many such records would be present given that the disk block size is 512? So there's Sanvi who says that answer is 15. Is there anyone who agrees or disagrees with this? So we have established that there are some n number of blocks, each of size 32, n number of records, each of size 32 bytes, and one block pointer which is of size 12 byte. Now, and this needs to fit into 512 bytes.
Sir, 15.
Right. So the answer is 15. And the solution for this is very trivial. So you have disk block size as 512 and disk block pointer as 12 bytes. So the actual storage would be 512 minus 12, which is 500 bytes. So it is only in these 500 bytes where you can accommodate the records. Okay, so the number of records would be floor of 500 by 32, which is 15. For all those who do not know what floor is a function that returns an integer less than or equal to the input. So if this calculation resulted in 15.5, for example, then what is an integer which is less than or equal to 15.5? That is 15. So you throw away all the everything after the decimal point and only retain everything before that. So you get the answer as 15. Is this understood? Okay. So moving on. Suppose that the record of a block in a library is 300 bytes long. The details of the disk storage is given. The disk unit rotates at 7200 rotations per minute. The data transfer rate of the disk is 75,000 bytes per second, whereas seek time is 20 millisecond. One block contains 5 such records of the book. If a student asks to know the details of a given book, how much time will be required to know that? Okay, so there's someone who says that B is the correct answer. Is there anyone with a different answer? Is there anyone who needs more time to solve this question? This is a slightly involved question, so it's very much valid if you need more time. Okay, so let's look at how do we approach this question. So first of all, if you want to access a record in a block, what are the three major components that that are involved in reaching the record? So first of all, there's this read write head that needs to move to the appropriate position. So this is what we call as seek time. So the read write head would have to move uh, to to a certain distance from the center of the stack, and this is the seek time. Now once the read write head is at the appropriate position, then the disk rotates, and this rotation is responsible to bring uh, the start of the block under this read write head. Okay, so the first component was seek time, where the read write head was to move until it achieves an appropriate distance. Then the disk rotates and brings the start of the block under the read write head. So this is the rotational delay. And once the rotational delay has been taken care of, the actual data needs to be transferred, and this would happen through the transfer rate, according to the transfer rate. So is it clear what are the three components involved? Seek time, rotational delay, and block transfer time. Is there anyone who wants me to repeat this? Okay. So if this is fine,
Please sir, again repeat.
yeah, okay. So, all right. So, do you know the architecture of how data is stored? So you essentially have a stack of disks. You have several disks which are stacked on top of each other. Each disk might store data on the top as well as the bottom of the disk. Okay, so there's like a stack of disk, and there's a head that that goes between these disks and reads data. Okay, so the data is stored on circles on the disk. So something like circles. Okay, these are called tracks. So what you are essentially required to do, you move the read write head at an appropriate position so that you are at a circle. Okay, on one particular circle. Now what you need to do, so the data can be anywhere on the circle. The read write head can only move like this. It cannot move like this, so it cannot go anywhere on the disk. It can only move uh, like this, so left or right. And once it takes an appropriate position, then the disk can rotate and bring the data underneath the read write head. So the read write head would have the data underneath it. So do you get how this reading is done? Read write head moves like this. It moves to an appropriate radius, and then the disk rotates and brings the block underneath the read write head. So is this understood? Uh, okay, I'm not sure if the student who asked understood this.
Yes.
Okay, fine. So what are all the operations that happened? The read write head had to move. Okay, and this is called seek time. Then the disk had to rotate. This is called rotational delay. And then once the read write head is on top of the block that you're looking at, you'll have to send all this data back. And sending of this data is called block transfer time. Okay, so three components: seek delay, rotational delay, and block transfer delay. Okay, so three delays that we are looking at. Now, okay, so let's get to the solution then. So the access time is the sum of these three quantities. Now seek time is very straightforwardly given to you, that is 20 milliseconds. So that is what is written over here. Now rotational delay is not actually given to you very precisely, because you do not, so a rotational delay would actually depend on where your data is on the selected track. So does the disk rotate entirely? Does it rotate only 45 degree or 90 degree? That is not given to us. Okay, so if the precise position of the block were to be given, then precise value of rotational delay could have been calculated. But because we do not know where what is the exact position of the block, what we would be doing is we'll be looking at average rotational delay. So on an average, how much does a disk rotate? So average rotational delay would be 1 by 2r, where r is the rotational delay, uh, or the rate at which the disk rotates. Okay, so this would be, so it says that what does the rotational delay mean, or the rotation speed mean? That a disk is capable of rotating 7200 times in a minute. Okay, so if it can rotate 7200 times in a minute, how many times can it rotate in a second? So it would be 60 over 7200. Okay, but these are complete rotations. But on an average, a disk would rotate only half, right? Because that's an average case where it does not rotate entirely but rotates half. So therefore, the average rotational delay would be 60 over 2 times 7200, which turns out to be this quantity. And then the block transfer time would be, you need to read an entire block. So you'll be reading 5 times 300. So there are 5 records, each of length 300. So 5 times 300 byte. And the transfer rate is 75,000 byte per second. So the amount of time taken to transfer 5 times 300 byte would be 5 times 300 over 75,000, which comes out to be 0.02. If you add all of these quantities, you get something which is close to 44 millisecond. So option B is correct. So this question is slightly involved. So if it's not clear, you can let me know right away and we can again revisit this question.
So the theory of this question from we get where we get the theory about this rotational delay and the time seek.
Okay, so I think it must be covered in the class where which shows that how data is stored on disks. Okay, the part which deals with magnetic disks, I think. So over there, you would see how data is actually read. So you might not really get all the formula that we have used over here. These are not even formula, right? These are commonsensical things. So you can find the mechanism. I think the mechanism would be discussed in the class, and then other things are quite intuitive. If they are not intuitive, you can let me know. I can discuss that once again, or as many times as it takes to explain the same to you. Is the mechanism clear as to why are the calculations the way they are? Okay, so Sanvi says that the theory is done in lectures. So in that case, I think you can also revisit the lectures once and get things clarified. Okay, so if this is clear, can we move to the next question, or are there any doubts in this? Okay. So moving to the next question. What is the availability of a database management system having the following reliability parameters? The mean time between failure, that is MTBF, is 36 days, and mean time to repair, MTTR, is 18 hours. The question is, what is the availability of a database management system? Okay. Okay, so we have two answers, C and B. Is there anyone who has a different answer? Okay, is there anyone who needs more time to solve this question? Alright, so let's discuss the answer then. So the correct answer is C, that is 97.95%. And I think, so without getting into any formula, let's try to make this intuitive. So we want to see what percentage of time is a database management system available for us. Okay, so that is what we want to find. So if I were to use a database management system, what is the probability that I find it operating and not in repair? Okay, so how much time is the system on and working? That would be mean time between failure, which is 36 days. Okay, which is 36 into 24 hour. Okay, so me finding the database management system is on an average 36 times 24 hours, and me finding the database system in repair is 18 hours. So if the database system is operating for 36 times 24 hours, and if it is under repair for 18 hours, what fraction of the time is it actually operating? It would be 36 into 24 divided by 36 into 24 plus 18, right? The total time is 36 into 24 plus 18, out of which 36 into 24 times the database system is available. So let me show you the solution. So if you look at the last equation, the numerator is the amount of time it is up, and the denominator is the total time, that is 36 times 24 plus 18. And this results in 97.95%. So therefore C is the correct answer. Is this okay, you want me to repeat? Fine. So when you look at availability, what does availability mean? That if I were to access this database management system, what is the probability that I would find the database management system working and not in repair? Okay, so is this interpretation correct? Understood of availability? Yeah. So you find that you want to find what is the probability of finding the system working. So what would be the probability of this? It would be the amount of time it works divided by total amount of time. Correct? What is the amount of time it works? It works for 36 times 24 hour. Okay. What would be the total time? The total time would be the amount of time it works plus the amount of time it is in repair, which would be 36 times 24 plus 18, right? As is given in the in this formula. So it's the numerator is the amount of time it is up divided by amount of time it is up plus amount of time it is down, and then this gives you 97.95%. So the percentage would not make it as intuitive in the form of probability. If you were to convert this into probability, it would be something like 0.9795, right? So I hope this is understood. Yeah. Thank you. Okay, so let us move to the next question. Suppose that a disk drive has 200 tracks numbered 0 to 199. Okay, the queue of pending requests in first in first out order is 75, 142, 93, 177, 48, 150, 102, 171 and 136. The read-write head is initially on track 45. What is the total distance that the disk head will move to satisfy all pending requests following the first come first serve scheduling algorithm? So the question is essentially how much movement would happen when you move from 45 to 75, from 75 to 142, from 142 to 93 and so on. Okay, we already have an answer B. Not even a minute and there are answers ready. Okay, so we have two candidate answers. One is B and the other is C. Okay, anyone who needs more time with this question? Okay, so let's look at the solution for this, which should be quite easy to understand. So maybe I'll first discuss this. So if let's say you're initially on 45 and you want to move to 75, what is the distance that you would be traveling? It would be 75 minus 45. That would be 30, right? Okay, so from 45 to 75 you traveled 30. From 75 to 142, how much did you travel? 142 minus 75, that is 67.
67.
So that is exactly what you need to do. So you need to take the difference between consecutive numbers, rather the absolute value between, because distance can never be negative. So you have to take the absolute value of the difference, add them all up, and what you get is 613. So is this understood? Okay. Alright, moving to the next question. Suppose that a database management system uses the most recently used, which is called as MRU strategy, as its buffer replacement policy. Further, suppose that the system allocates 4 free buffer blocks for execution of a query to be used as a buffer. Assume that the query requires to access the following disk blocks in that order to complete its execution. Calculate the number of block replacements when all blocks are full. A residing block is replaced with a required block. So you need to calculate the number of block replacements required to complete the query. So essentially you're using the most recently used strategy for replacement, and you have 4 free buffer blocks, and this is the order in which you're accessing. Okay, so how many block replacements would be involved?
Option B.
Okay. Is there anyone who needs more time? Okay, so there's someone who says option C. Okay, again option C. Okay, so it seems that B and C are the most popular choices over here, and they're quite close, so it's quite easy to miss one or get one extra. So let's look at what the correct answer is. So the correct answer is 8. Okay, so this is a table which is an elaborate way of showing how these replacements would be done. So you initially have all the 4 blocks empty and all the 4 buffer blocks empty, and then 9 is accessed and is added to the buffer block, so you have 9 over here. Then 5 is accessed, 5 is not in the buffer, so it is also placed in the buffer. Then 1 is accessed, 1 is not in the buffer, 1 is placed in the buffer. Similarly, 2 is placed in the buffer. Now when a request for 5 is made, you see that 5 is already available, so you return that value. Now you a request for 3, but 3 is not available in the buffer that you have. So what you do is you replace the most recently used, which is 5. So instead of 5 you put 3, and therefore this amounts to 1 replacement. Then afterwards there's a request for 5. Now 5 is not available. So what replacement policy do you use? You use most recently used. The most recently used was 3. So you replace 3 by 5. So that amounts to another replacement. Now if you keep continuing this, you would notice that the number of replacements that are done is 8. Okay, so once the slides are posted, probably you can just take a look at this and see if this convinces you that the correct answer is 8. If there are doubts, we can also discuss this in the next tutorial. So apart from you going through this slide, Are there any questions about the setup of the question? Okay. So in that case, we can move to the next question. So consider the following statements. The first statement is copy the required block from the disk to the main memory buffer. The second statement is the program calls the buffer manager for the required block. The third is buffer manager returns address of the block residing in main memory to the program. And the fourth statement is replace some other block if the buffer block in main memory are not free. The question is, arrange these statements in order to resolve what happens when a program identifies that a required block is not available in the main memory buffer. Okay. Alright, so one thing I think is agreed upon is that the buffer calls the buffer manager for the required block. So the second statement should be first, I think is pretty obvious. Correct. Now, what I think should also be obvious is that option 3, statement 3 should be the very last, because the buffer manager returns address of the block residing in main memory to the program. So returning the address should be the last step. So the answer would begin with 3 and would end begin with 2 and would end in 3. Okay, so if that is understood, then the question is which one of 1 and 4 should be kept first. Okay, so yeah, Karthik here actually identified the correct answer, which is 2413. So first of all, you would have to create some space for a block to be fetched and put in main memory buffer, right? So therefore 4 needs to be executed first. So you would have to replace some other block if the buffer blocks in main memory are not free. And once you have replaced, then you can copy, replace or rather discarded, then you can copy the required block from the disk to the main memory buffer. So therefore 4 happens first and then 1 happens. So to summarize, the program calls the buffer manager for required block. If the buffer block in main memory is not free, you would have to create some space. Once the space is created, you copy the required block from the disk to the main memory buffer, and finally return the address of the block residing in main memory to the program. Is this understood? First step is the program would call the buffer. Second, you check whether there's space. If not, you create space. Then copy the block to the buffer and then return the address. Okay, so 2413 is the correct answer. Are there any doubts in this?
No, sir.
Okay, thank you. So let us move to the next question then. Consider the following schema where you have two schemas actually. So the first is member with several attributes and journal publication with several other attributes, and then you are given these functional dependencies. What I would urge you to do is take a screenshot of this, because this would be required for the actual question. So I'll show you the answers later on. The question, so you'll be given some schema, okay, and you have to identify which one would be the refined optimal schema for these. Okay, so I hope everyone has taken a screenshot of this slide. All right, so then here are four options. Which of these options would you regard as optimal? Okay, so when we talk about optimality, what are we actually talking about? We want to remove redundancies, and we want to use as little storage as possible. So we can immediately see that option A and option C have this extra information about journal list, which is uh, a table comprising of only two attributes, DOI and MID, right? And why is this redundant? Because in both the options A and C, if you look at the table member, it still has member ID and DOI. Correct. So the functional dependency, which you must have, you can see in your screenshots, MID determines DOI. So that is already captured in the members table. So you do not need an additional journal list table for the same. So therefore option A and option C are quite wasteful, or they use excess space. So is it clear why option A and option C can be discarded? Okay. Now option D can also be discarded. Can someone guess why? So option D can be discarded because it is not dependency preserving, as in neither in table member nor in table journal publication do you preserve the dependency MID determines DOI. Correct. So probably if the members table had the attribute DOI, then you could have said that this is dependency preserving, but it is not the case. So therefore option D is also incorrect, which leaves us with option B, which happens to be the correct answer because it takes less space and also preserves the dependency MID determines DOI through the journal publication table. So you can see that in journal publication you have both the attributes DOI and MID, and therefore the dependency MID determining DOI is preserved in this table. So is this clear why B is the correct answer? Okay. So let us move. Here is an explanation. You can refer to it offline. Okay. So here is the next question. Suppose you have a 128 gigabyte flash storage system with a 2048 byte page size. How big would the flash translation table be, assuming each page has a 32-bit address and the table is stored as an array? Okay. So there's one student who says that A is the correct answer. That's a very big number. But see, you have a total storage of 128 GB. Okay. And the page size is 2048. So essentially, what is happening is these pages are like small segments in the total 128 GB size storage. Okay. So there are 2048 sized pages in 128 GB. Now you want to create a translation table which has the starting address of all of these pages. So what would be the size of such a table? So translation table is a table that contains the address of each page. So what would be size of such a table? Okay. Okay, so let us look at how do we solve this question. So like we discussed, the size of the what flash translation table would do is uh, contain the address of all the pages. Okay, so if there are n number of pages and each page has the address of each page is 32-bit, so what would be the size of this translation table? It would be 32-bit times n. What is 32-bit? 32-bit is 4 byte, correct? 32 by 8. So it would be 4n bytes, the size of the translation table. Now what is the value of n? How many pages do you have? So the total amount of storage is 128 GB and the size of each page is 2048 byte. So the number of pages would be 128 GB divided by 2048B. So the size of the translation table would be 4 byte into 128 GB divided by 2048 byte, which turns out to be 256 megabytes. So let me show you the answer. So the number of pages is 128 GB by 2048 byte, which is 64 mega. Okay, and each page is 32-bit, which is the same as 4 byte. So to convert bits to bytes, you have to divide by 8. Okay, and finally, so therefore the array size would be 64 mega into 4 bytes, which is 256 megabytes. Is this understood? Okay. So then let us move to the next question. Choose the incorrect statement from the following. Data dictionary stores the information about schema definition. Data dictionary stores the information about integrity constraints on a relation. Data dictionary does not store user and accounting information of a database. And data dictionary stores information about file organization. So the question is to select the incorrect statement.
Option C.
Right. So option C is the incorrect statement. And here is an explanation as to why the other statements are correct. And a reference to the lecture slides is also given. So I think because this is a theoretical question, you can also refer to read through this slide offline. And if there are doubts, you can also refer to the lectures. Okay. So let us move to the next question then, which is again a theoretical question. So the different uniform resources used to identify and locate web resources in the web are URI or Uniform Resource Identifiers, URL Uniform Resource Locators, and URN Uniform Resource Name. Find the incorrect statement from the following regarding URI, URL, and URN. The first statement is URI can either be URN or URL or both. The second statement is URN identifies a web resource by its name given in the namespace. The third option is URL provides the functionality of a pointer to locate a web resource in the web. And the last option is URL defines something's identity while URN provides a location.
Option B is incorrect.
B or D? You can say first, second, third, fourth. Okay, so I think everyone agrees that option D is incorrect, and that is indeed the case. So I think again, because this is quite theoretical and not much involved when it comes to explanation, you can just refer to the solution given over here, and if you have doubts you can refer to the class slides. Okay, moving to the next question. Consider a table which contains the salary of employees. A new salary of 15,200 is inserted into the table, after which the pointers are rearranged as shown in the figure. Which of the following file organization is used to represent this? The first option is sequential file organization. The next is heap file organization. The third option is multi-table cluster file organization. And the last is hash file organization. I think this is also straightforward question.
Option B.
Okay, anyone who disagrees and thinks it's a different option? Okay, so if you recall, I think it was the very first question that we solved today about unspanned and sequential style of storage. And in that, we saw that sequential file organization is where you have data which can be a single record or multiple records followed by a block pointer. And then these and then you connect the block pointer to the next block, which again has some data and a pointer, which is like a linked list. Correct? So for all those who are familiar with linked list, which is a data structure to store sequential data given non-contiguous memory. So you have data followed by pointer. The pointer points to the next data and the next pointer. So this is also very similar, right? So you have salary information and the pointer to the next. And therefore this is sequential file organization. Does that make sense? So again in the slides there's like a very rudimentary definition given for all the other styles of file organization, but I think in the lectures there's like more fleshed out examples that are given. So just to get things more clarified, you can refer to the lectures to see what are the other types of file organization. Okay, but I hope it's clear that this is sequential because there's data followed by a pointer to the next record. Okay, so let us move to the next question then. If a disk system contains 1600 disk drivers and each has a 4 lakh hour mean time between failure, how often a drive failure will occur in that system? So you have 16,000 disks, each has mean time between failure as 4 lakh hour. So how frequently would disks fail? Okay, so there's one answer, that is 250 hours. Is there anyone who disagrees or has a different answer? Okay, again D. Okay, so D is indeed the correct answer. So mean time between failure can be interpreted as a probability that given a disk, the disk is likely to fail once every 4 lakh hours. Okay. Now, if there's one disk that fails once every 4 lakh hours, and you have multiple disks, then and you want to look at disk failure in the system. So what would be a disk failure? A disk failure would qualify as the first disk failing, or the second disk failing, or the third disk failing, and so on until the 1600th disk failing. So therefore, you would add all these probabilities by the law of probability addition. So you would add 1 over 4 lakh 1600 times, which would give you 1600 over 4 lakh. So this is the probability of failure in the disk system. So what would be the time? It would be the reciprocal of that, which would come out to be 250 hours. Or simply, you can use this formula, that is, given a system, the mean time between failure of this system would be the mean time between failure of one disk divided by number of disks in the array, which is 4 lakh divided by 1600, which is 250 hours. So is this clear, or should I repeat? Okay. So then let us move to the next question. Consider a disk pack with the following specifications: 16 double-sided platters, 256 tracks per surface, 512 sectors per track, and 1024 bytes per second. Which of the following is correct capacity of the disk? Is it 512 MB, 2 GB, 4 GB, or 8 GB? Okay, so there's one answer, 4 GB. Just keep in mind that the G and B both should be capital, because a small b is used to represent bit and not byte. Okay, and I'm not sure if there's a small g. So yeah, both should be capitalized. So to fully understand the question, you again need to be aware of how a disk looks like. So like we discussed, a disk can have you'll have several platters. In this case, you have 16 platters, which are double sided, as in you can store data on the top as well as the bottom. Then there are multiple circles on each platter. In this case, you have 256 tracks per surface. Okay, so 16 of those with two sides. On each side you have 256 circles. In each circle you have 512 sectors. So sectors are like pizza slices, like this. And then in each sector you have 1024 byte. Okay, so how much would be the storage? So first of all, if you are aware of this, the way in which these blocks are distributed across a disk, then that's great. Otherwise, there's a shortcut, which is to look at the units. So you're given 16 double-sided platters. So this would be 16 into 2 surfaces, right, which is 32 surfaces. Then you're given 256 tracks per surface. Then 512 sectors per track, and then 1024 byte per sector. So if you multiply all these units, you would see that what you end up with is only bytes. Okay, and that indicates that you are indeed supposed to multiply all these units to end up with only bytes. So what would be the correct answer? It would be 1024 byte per second, byte per sector, times 512 sector plus track per track, times 256 track per surface, times 16 into 2 surfaces, and that comes out to be 4 GB. Okay, so this is the answer. This is slightly complicated looking, but it is essentially this exact same thing. So is this understood, or do you want me to explain this again? Are there any doubts in this? Okay, so if this is fine, then we can move to the next question, which is again theoretical. So if you want to design a secure database application with large amount of data and low update rate, which of the following rate level would you select? So since this is a theoretical question, I'll just give away the answer, which is A. Again, for more details, you can refer to the course lectures. Okay, we'll move to the next question. So in a cafe shop, several types of food items are available. A customer places his or her order. A serviceman can serve multiple orders, but an order will be serviced by only one serviceman. A customer can place more than one orders. Which of the following statements is or are true? There will be minimum 3 entities in the ER diagram. There will be minimum 4 entities in the ER diagram. Minimum 2 relationships will be required in the ER diagram to model the scenario. Minimum 3 relationships will be required in the ER diagram to model the scenario.
Option C.
Okay, option C is correct. And what about the number of entities that would be required? Okay, so you definitely need two relationships. One relationship would be placing an order, and the other would be serving. Okay, and what are the entities that are involved? The entities would be uh, definitely a customer and a serviceman. But then the customer would place an order, so order would be another entity. And what does an order comprise of? It comprises of food, so food would also be an entity. So therefore you'll need four entities in the ER diagram. So option B and option C are correct. Is this clear? Okay, so let us move to the next question then. Consider a sequential file for the relation customer. The record size is fixed and the size of one record is 46 byte. If the records do not cross boundaries, that is, this is unspanned organization, and the disk block is 512 bytes with block pointer size 10 byte, what is the maximum number of records that can be stored in one block? I think this is similar to the very first question we did, so you should be able to answer this question correctly. Okay, so we have one answer which is 10. Anyone else? Okay, we have C also as one answer. Okay, so let's see. So we saw that the disk block size is 512 byte. And what does this block contain? It contains multiple records and exactly one block pointer. So let us say that the total number of records is n. So this 512 should be greater than or equal to 46 times n plus 10, because there are n records, each of size 46. So the total size would be 46n, and the block pointer is 10. So 46n plus 10, this should be less than or equal to 512. And if you solve this, what you end up with is n can be at max 10. Okay, and therefore the answer is 10. Is this understood? Any doubts?
No, sir.
Fine. So let us move to the second last question. An operating system uses least recently used strategy for replacing its buffer. Suppose the system allocates 3 free main memory buffer blocks for the execution of a query. if the query requires the following disk blocks to access its completion, to complete its execution. So here is the list of blocks. What would be the image of those three blocks after servicing the disk block 9? So once 9 has been requested and serviced, how would these three buffer blocks look like? Okay, so we have two answers, A and B. So keep in mind this is least recently used in contrast to most recently used from one of the previous questions. Okay, so there's one answer which says that D should be correct. Is there anyone who wants to revise their answer? Okay. Alright, so the correct answer to this question is actually D, the fourth option. So let us look at how the answer is D. So first of all, you have three buffer blocks which are initially all empty. Now you request for 2, which is not available, and all the blocks are empty, so you place 2 in an empty buffer. Then there's a request for 5. 5 is not present in any buffer, and there's an empty buffer, so you place 5 in the empty buffer. You request for 3. 3 is not available in any buffer, and there's an empty buffer, so you place 3 in an empty buffer. Now there's a request for 5. 5 is available, so return 5 directly. Then there's a request for 4. 4 is not in the buffer. There is no empty buffer, so you have to create space for 4. So which record do you decide to delete? You decide to delete 2 because that was the least recently used. It was accessed least recently. So therefore 4 replaces 2. Then there's a request for 5 which is available, so you return 5. Then there's a request for 3. 3 is available, so you return 3. There's a request for 2. 2 is not available. There is no empty block. So therefore we need to create space for 2. Which block should be replaced? The block that is least recently used, which is 4. So therefore you end up with 2, 5, 3. Finally, there's a request for 9. 9 is not available. There is no free buffer. So therefore you need to create space for 9. And which buffer should you clear up? The one that was least recently used, which is 5. So therefore you replace 5 and end up with 293. So is this understood? Why is the answer D? Are there any doubts? Okay. So if that is understood, let us move to the last question. So the last question is, which of the following statements are false about the buffer manager? The first option is programs call the buffer manager when they only need to transfer a block to disk. The second is, if the block is already in the buffer manager will do nothing. The third option is, if the block is not in the buffer manager allocates space in the buffer for the block. The last statement is, for allocating the space, sometimes the buffer manager replaces some other blocks. So the question is, which of these statements are false? Okay, so we have two answers, B and C. Okay, so B seems to be a popular option. So if the block is already in the buffer manager will do nothing. So that is not the case. If the block is already in the buffer, then the buffer manager would return the address of the block. Correct. So B is definitely false. You can see that option C and D are correct actually. So if the block is not in the buffer, then the buffer manager somehow tries to allocate some space in the buffer. So it can do that by replacement. Like we saw, there are possible strategies such as least recently used and most recently used. So if a block is not present, the buffer manager can allocate some space in the buffer for the block using some strategy. Okay, so C is correct. And D also fits into the same narrative because to allocate space, the buffer manager might have to replace some blocks. Okay, so that's also true. What about option A? Is it only the case that when you need to fetch something from that a block needs to be only transferred to the disk and then you call buffer manager? No, that is not the case, because if the requested block is in the buffer itself, even in that case the program would call buffer manager. So the program does not really bother where the data it wants to fetch is. It just calls the buffer manager. Now the buffer manager could fetch it from the main memory or from the buffer. Okay, a disk or the buffer, and that that is not a concern of the program. Correct. So therefore, the first option is also incorrect, because if the data is present in the buffer also, then the buffer manager would be responsible. So therefore, option A and B are incorrect. Okay. So here is again a brief explanation which you can go through offline. So with this, we come to the end of this week's tutorial. If you have any doubts, you can let me know. Else, you can feel free to drop out of the meeting, and we'll meet in the next week. Okay, so until then, I wish you a very happy weekend and see you next time. Thank you. Thank you. Okay, so if there are no more questions, I'll just end the meeting then. Thank you, everyone.